we are going around digging holes, right? Like just trying to poke around for something where the standard model breaks.
It's not black holes, it's not, wadded up socks in interstellar space, it's not rocks, it's not dust particles.
You just cannot solve within the framework of the theories that we currently use. You need an entirely different type of theory.
The laws of physics learn how to be the best laws as the universe evolves.
An issue with physics, which I think many people, even outside of the field, will be probably aware of, which is that here's our most successful, most powerful theory, almost in all of science, quantum mechanics, the theory of the subatomic world. So powerful, so successful. Without it, we wouldn't understand so much of the modern world. We wouldn't be having this discussion, certainly, on a computer, because we wouldn't have understood and developed modern electronics. So quantum mechanics works, and it's brilliant, and it describes our universe on a tinier scale. And yet, somehow, we've managed to get away with not having a single agreed upon narrative, interpretation, story of what the mathematics means.
Everybody has an attitude with respect to quantum mechanics. It's a little bit like, what's your religion?
Yeah, that's right. It's interesting, isn't it? And we try, as particularly as physicists, to say, no, we are objective, we don't follow physics isn't an ideology, as I'm sure you did, as probably all physicists of our generation. We were trained, we learnt quantum mechanics following the standard, the Copenhagen view, the textbook view. While I haven't fixed on one particular interpretation to say that yes, it's definitely many worlds, there are many universes, this is I subscribe to this dogmatically. The one view I do feel strongly about is that it cannot simply be a matter of philosophical taste or choice, how we think nature is. We have an embarrassment of these different interpretations, the way we explain what the maths tells us about the world, whether it's Copenhagen, whether it's relational, whether it's quantum Bayesianism, whether it's many worlds, whether it's de Broglie-Bohm. There's all these wonderfully named exotica, all strange in their own way, all easy to argue against from another perspective, because every one of them has some strangeness in it. My view is that one of them has to be right and the others are wrong, because I think nature behaves in a certain way independently of our debates and arguments and discussions. Either there are parallel universes or there aren't. Either there are hidden variables or there aren't. Either the universe is deterministic or it's indeterministic. I tend to be, if I'm asked to sort of pick one that I prefer, I tend to prefer sort of the more realist interpretations. There's an objective reality, which I guess probably goes against relational quantum mechanics, because that would say that an atom doing what it's doing something. Regardless of you and I having different views on it, it's doing something, and quantum mechanics should tell us what it's doing. It's been behaving quantum mechanically before humans arrived, life emerged 4 billion years ago on Earth, and so it can't simply be a world that's somehow conjured into crystallized into reality by our observations. So it may be that sits underneath. Maybe relational quantum mechanics is all quantum mechanics can tell us. It can, how we perceive the world, but maybe underneath that there is some objective reality that we may or may not ever one day reach. But I sort of feel that it has to exist there independently of our observations.
The mystery is, but what about the classical world? Aren't we made of atoms, and aren't we quantum as well? There's a remarkable difference of opinions in the community. Each one of them has a very high philosophical cost. They ask us to realize that something we thought before was wrong, that there is more in the world than what we just see. Maybe there are hidden variables that we can never measure. Maybe there are other words. Maybe there is a... So the question now is which perspective is more useful? And the debate is open, and I think it has been changing. The relational quantum mechanics you mentioned, on which I've been involved, is probably the young kid on the block. Is much younger than the others. It's very close to Copenhagen and to the standard textbook. In fact, I would say is the closest tentative solution of the problem to the textbook one. The textbook, what you write in textbook is that you study a quantum system, but you're outside it, you're in a classical world, a non-quantum mechanical world. So you describe how the system affects you, the classical world, how it affects your apparatus, what you measure, what you see. And it works very well. And the mystery is, but what about the classical world? I mean, isn't quantum mechanics as well? Aren't we made of atoms? And aren't we quantum as well? So how can we have a theory that explain how quantum stuff affect us, classical stuff, if we are ourselves a quantum? Now, the relational idea is very simple, and is the following. The theory is not telling us how a quantum system affects the classical world. The theory is telling us how a system affects any other system. Any two physical system, that don't need to be human, don't need to be memory, to be classical, anything. If you want to know how one effect affects the other, you use quantum mechanics. And this is intense because instead of thinking of system with properties, you only are asked to think of systems with relations with others. So in a sense, systems by themselves don't exist. They only exist in the way they affect the other. That's the idea. And it has a technical side. I'm defending it. And the main argument in favor of it I have is that the alternatives are even worse.
Is there a sense, do you think, that we need another paradigm shift? Maybe not another Einstein, but another collective switching to look at the reality in a different way?
We don't need a new idea. We need to clarify the incredible steps ahead that have happened 100 years ago. Generativity is an incredible step ahead in our understanding of the world. And quantum mechanics is an incredible. And we just have to digest all that. Like Europe had to digest the Copernican revolution. Newton was certainly capable of repackaging everything that was found in the Renaissance in a coherent way and opening the way to development. But there have been further repackaging. Field theory has been a complete repackaging. Maxwell and Faraday have just changed the way of thinking about what reality is made of. I think quantum mechanics requires us to change the way we think reality is made of. And so is generativity, because space and time are pretty basic in our pre-generativistic. So I think we're in the middle of that. It's not that we need something new.
Nobody put it in by hand. It's not like somebody says, you know what, I'm bored, I want to put this thing in, so let me just change my theory so it has gravity in it.
So what kind of significance or consequences does string theory leave? Why should we care about string theory today?
Well, it is the reason we care about string theory is that we believe Einstein had the correct description of gravity, which is a geometric picture of how gravity works by the curvature of space and time. On the other hand, we also know at the microscopic level, the tiniest level, quantum mechanics is important, how the atoms work. Since we know quantum mechanics is a fact of life in the real world, in the microscopic regime, and Einstein's theory seems to be correct in a macroscopic description of gravitational forces, well, if you take Einstein's theory and take it to the extreme of smaller and smaller, shorter and shorter microscopic descriptions of it, you better have a consistent theory with quantum mechanics. And there is no other framework today which is consistent with Einstein's theory and quantum mechanics at the same time. String theory is the only candidate we have which combines Einstein's theory with quantum mechanics in a consistent framework.
And how is it that it brings about that gap between Einstein's theory and quantum?
It is actually one of the miracles. We don't understand how it does it. What we found is that if you study these vibrating strings, which are these excitations that we have, one of the little modes that these strings have, which is very tiny strings, turns out to have exactly the same properties as mediating gravitational force. That is, that exchange of this little thing between other particles mediates gravitational force between them. Why it had to have this property is not clear, but it turned out that this theory just does it. And so many things in string theory, we don't understand why it works, and it's really magical. And part of the reason we believe in it is that nobody put it in by hand. It's not like if somebody says, you know what, I'm bored, I want to put this thing in, so let me just change my theory so it has gravity in it. No. People started studying string theory and they say, oh, there's gravity in this. I didn't put it in. Where did that come from? So it gives more credibility to the theory. It's kind of brings out things we want to have without actually putting it in. So we believe that's one of the beautiful aspects of string theory, this magical property, that things that you get out of it are more than what you put in.
And what would opponents to string theory, what are the biggest problems with the theory?
So the opponents would rightly point out that there has been zero experimental verification of string theory. String theory is a part of science, and all science should be vetted by experiment, no doubt. So why haven't we had experimental verification of string theory? Well, part of the issue is the size of the strings by theory is 10 to the minus 30 centimeters or smaller. And just to give you a scale, that's 10 to the 22 orders of magnitude smaller than the size of the atom. So you put 10 to the 22 strings next to each other, 10 to the 22, that's billions of billions of billions next to each other, roughly, something of that order. There's a huge number just to get one atom out of it. So it's very difficult to zoom in to that small space to see that string. So therefore, naturally, you're going to have difficulty measuring experimentally verifiable aspects of it. Of course, we're trying to, nevertheless, try to deduce some experimental aspects of string theory, which could be observed and be an irrefutable sign of string theory. It's going to be very difficult, and we have some ideas, and in particular in the context of cosmology, we're coming up with a few ideas. For example, that's one of the areas that I have, for example, and a few of my colleagues have been very interested in recently, trying to understand the nature of the dark energy. What is the dark energy made of? We also have dark matter. So most of the universe, in terms of energy, 95% of it is in the form of dark energy and dark matter combined. And our visible universe, our matter, is just 5% of the all of the universe energy. So what is this 95% made of? Well, string theory seems to offers new ideas about what this is and how they interact. What is the relation between dark energy and dark matter? So one of the prevailing views up to now has been that the dark energy, the energy that permeates all the universe, is constant and doesn't change with time. Recent ideas that I've worked on with my colleagues as of a year ago suggest that the energy of the universe may actually be changing over time. And if the energy of the universe is going down, for example, you see that the acceleration of the universe will change. And the idea is that the acceleration of the universe in the recent past has been changing, and therefore by detecting how the light you get from supernova and other astrophysical objects, you can detect the rate of expansion and whether it's slowing down or not. And based on that, you can find whether dark energy is depleting or not. So those would be new signs of connecting string theory to observed universes. So there could be different ways we could potentially be successful in getting experimental consequences out of string theory.
The actual problem comes down to saying there are certain types of initial conditions which we do not like. So to answer the question, is it time to give up on our theory of antimatter? I think the answer is no. And to see why, I have to briefly explain how all our current theories work in the foundations of physics. You have something that's called the initial condition. That's a summary of all the information about the system that you're trying to describe. So in this case, it would be all the particles in the universe and the universe itself. And then we have something that's called an evolution equation, which acts on that initial state and tells you what happens at all other moments in time. And the theories that we currently use, they all work the same way. So you need this initial condition to make any prediction with the theory, but the theory cannot itself predict the initial condition. And when we say that the universe should have been, self-destroyed within a blink of an eye, what this means is that we have made an assumption about a particular initial condition. In that case, it's that there are exactly equal amounts of matter and antimatter, and those should have destroyed. But it's very easy to solve the problem by just choosing an initial condition that agrees with what we observe presently. And that's actually what people also do when they work with these theories. So the actual problem comes down to saying there are certain types of initial conditions which we do not like. And I don't think that this is a serious problem. What some people think is wrong is that they do not like that this initial condition must have been so that there was a tiny little amount more of matter than antimatter, because otherwise, as we already discussed, they would just have left behind a lot of photons, which is not what we observe. So the question is really in this, I dare to say, beautiful assumption of symmetry and charge conservation or what have you, which we don't know is correct. The assumption is the ratio was exactly 1.000000. Okay, and that does not agree with observation. Instead, the ratio was more like something like 1.000001. Okay, and I'm saying where one of these numbers is exactly as simple as the other number. Okay, so the people who think that there's something simpler about the last digit being a 0 than it being a 1 don't understand this requirement of simplicity. And without that, it comes down to an argument from beauty. And I don't think that's a scientific criterion, which is why I don't think it's a serious problem. The kind of theory that we currently use, like the Standard Model and also general relativity, they generally have a problem with certain types of questions when it comes to an initial value, like the ratio of matter to antimatter, but also other things. Like, for example, in cosmology, people are discussing the question, why is the curvature of our universe what it is? And that also goes back to a question of an initial condition. And there are lots of other issues like that, which you just cannot solve within the framework of the theories that we currently use. You need an entirely different type of theory.
That's a good thing for the universe, to have a little bit more matter than antimatter. I'd like to go a little bit further and contemplate what a theory that explained the amount of matter versus antimatter that we see in the initial conditions, because we're in, as Sabina emphasized, a situation where our theory is incomplete, in that knowing the laws of motion is only part of the physics, and the other part that you need to explain why our universe is the way it is, as Sabina said, the initial conditions. So how would we make a theory of the initial conditions? And related to that, how would we make a theory of all the parameters in the Standard Model that come in to phenomenon like the asymmetry between matter and antimatter? And I'll quote the American philosopher Charles Sanders Peirce in saying that the only way we can explain initial conditions or the laws themselves is if they're the result of some mechanism of evolution. If they change and there's some dynamical explanation for why that's a good thing for the universe, to have a little bit more matter than antimatter. There are two theorems that are essential to particle physics that are at stake here. And when you say something like there's a flaw, and should we be responding to the flaw, this is what you're really referring to. So let's put them on the table. There is a symmetry called CPT, which means take antiparticles, reverse the direction of time, and look in the mirror. And CPT is a theorem in a certain class of theories called quantum field theories that respect both the axioms of Einstein's theory of special relativity and quantum mechanics. If you believe those two theories are ultimately correct, then you believe that doing those three things must be like doing nothing. And that's relevant because of the role of C to turn particles into antiparticles. But to turn that into a prediction that during the growth of the universe, there would be an equal number produced, you need another assumption, as was demonstrated by Sakharov, who was one of the great Soviet theoretical physicists and cosmologists. And that's the assumption that the universe as it expands is always in thermal equilibrium, so that there's a balance equation as in chemistry. So the rate of production of particles is the same as the rate of production of antiparticles. And that's not necessarily true. And it's not difficult for the cosmologists to hypothesize and study scenarios in which during the expansion of the universe it was out of equilibrium. And that's all you need. You don't need to overthrow the foundations. I'm the guy who loves to overthrow the foundation. It's completely conventional to solve the problem by having the universe expand so rapidly in the early stages that it goes out of equilibrium for a little while. What I'm studying now is whether, and you're going to tell me I'm crazy, whether it would make sense to say that the laws of physics learn how to be the best laws as the universe evolves. Maybe much of this is before the Big Bang. And that sounds crazy, but let's note that we have these intelligent machines that we think can learn. And I'm staying far away from, are they anything like us? Are they conscious? I think we will admit that they can learn. And if I can code the instructions for one of these intelligent or learning machines in the laws of the Standard Model, then I can envision a situation where the Standard Model is what it is because it learned something about how to be a universe. And I know that's sounding provocatively crazy, but I think it's more, let me quote Feynman. If a whole lot of smart people have failed to solve a problem despite much, much effort, then maybe it's time to turn the problem on its head. And it might be that you discover it's an entirely different problem that does have a solution. And I do think that overall, the situation in fundamental physics is calling for new ideas and different ideas about what a theory is and how it relates to experiment. But I think we have, if we go there, then everything like this is at stake.
I'm going to say the thing that Leo has heard like 1 million times. If you have a law that changes, then you have a different law that tells you how the law changed. So it's again a law.
I'm only talking effective field theory. I'm not actually saying anything profound.
I'm an instrumentalist. Okay, if you give me a theory and I can calculate something with it and it fits to observations, I would call that a good theory. And there other people like to tell stories about what this mathematics means. Okay, it may be that the universe learns or the universe makes new universes and so on and so forth. And I would just say, well, that's a kind of an optimization problem. Okay, you can always look at it from that perspective, and that's fine with me. And I actually think that to move on in the foundations of physics, we kind of need a theory like that, maybe not exactly this, but something in this direction. Maybe so there's kind of a related idea has been put forward by David Deutsch, who has this idea of constructor theory. And I don't really feel confident enough to tell you exactly what this is about. But basically, he's saying that this route that we've been on in particle physics and in cosmology, that we're looking for explanations going to shorter and shorter distances and further back in time, may have its limits. And he's trying to say that maybe some of those explanations may actually be found on larger scales. And one of the examples that he's given to me is that maybe the laws of nature are so that they have to be Turing computable. Okay, so he's a computer person, so that's the kind of problem he would come up with. And that puts some restrictions on how the laws of nature are, but it's not something that you would find by going to shorter and shorter scales or asking about the initial conditions of the universe. It's a kind of explanation that we don't currently think about in the foundations of physics. And I kind of feel that we need some entirely new thoughts of that order of magnitude to move on.
In particle physics, we've been living in sort of this state of growing dissonance. We have made some absolutely stunning experimental discoveries in physics in just the last 20 years, which is pretty impressive because 2 decades isn't an extremely long time in the world of physics. So 2 really recent discoveries that come to mind that I think are relevant for our discussion are the discovery of gravitational waves that was long awaited, right, and confirmed Einstein's prediction from general relativity. And then, of course, there was the discovery of the Higgs boson. So both of these discoveries were highly anticipated and eagerly awaited. So, and they confirmed foundational theoretical work. So it would be difficult to say, I think, that the G-2 result from Fermilab is more significant. So I would instead say that that it may be one of the most transformational results of the 21st century. And transformational because unlike the 2 discoveries I just pointed out, it's shedding light on physics that's outside of our current theoretical frameworks, right? And so that's what's so compelling about it. And so in particle physics, we've been living in sort of this state of growing dissonance, right? How can the standard model of particle physics do such a splendid job of predicting something like the Higgs? In fact, predicting every single particle and finding that's within its framework, and also doing such precision predictions. So, for example, it can predict to parts per trillion, accurately predict to parts per trillion the magnetic moment of the electron, right? So how can an experiment, a theory that is on such firm ground also be completely agnostic about the things that we know, right? That there's more matter than antimatter. How can it have absolutely no idea where dark matter comes from? So we're living in this state of tension, and we've been living there for decades now. And it's just growing, and so I think this experimental results, which will only improve in precision because we only released 10% of our existing data, and this result, which is of course partnership with theoretical predictions, and they will also improve their precision. So these results will go forward and improve in precision. I think what it's done is it's really poked a hole in the darkness, right? That's what it's done. It's given us a guiding light to where we can start to go to resolve this tension. And what's exciting is once you see one pinhole, often other pinholes come up.
Why is this? Why have we already felt that we need something more than the standard model, which explains all the particles that we know about? And if that is the case, what might that extra thing be? And do we get any hints of it from this experiment?
A lot of our evidence comes from astrophysical signals. I mean the fact that we know we're dominated by dark matter, the fact that we have more matter than antimatter in the universe, the fact that we have no idea why there are 3 generations of leptons. Why is there an electron, muon, and a tau that only vary by their mass? I mean, no one, the standard model is agnostic on these things, and so we know that we're missing some piece, and so I feel like we are going around digging holes, right? Like just trying to poke around for something where the standard model breaks. So we were quite fine with breaking the standard model because that, like I said, it's a way to move forward.
All the fingers for dark matter point to a new subatomic particle and extension, something not in the standard model. The electron version of this moment is one of the most incredible precise results in physics, and its agreement with theory, with standard model, is to better than 1 part in a trillion. But in effect, at that level, and this is the leverage the muon provides by being more massive, and Renee can comment exactly on the downsides of the muon because it decays. Electrons are stable, much easier beasts to study in the lab or in an accelerator. So the muon, an effect that would be imperceptible at the 1 part in a trillion level for the electron is present at about a 1 part in a billion level, roughly, for the muon. So you just get a lot more leverage into these virtual antiparticle-particle pairs. And so you're tapping into potential, if new physics, obviously, in sense of new particles. And just to connect it back to the larger theme of our debate, we're searching for new particles. The dark matter particle is, we don't know what it is, axion, neutralino, whatever, there's candidates. And so the sense of this discrepancy, of course, is in the direction of some new, potentially new particle that could fit the bill for things that astrophysicists are keenly interested on. CERN has not found any supersymmetry evidence, not found other versions of the Higgs. There's been a bit of a dry spell there since that spectacular result almost a decade ago. So it's very poignant, the situation we're in, because there's some really amazing things that could happen if this really pans out. We've got some big, in astronomy or astrophysics, we've got some huge dirty laundry to deal with. We've got dark matter and dark energy, the two major components of the universe, with all of us in this room and all the planets and stars and galaxies in the universe being a few percent of the universe. That's pretty embarrassing. And we're grasping, so on both sides, I think we're sort of grasping for things here. And astronomers have these two big, profound mysteries to solve about the nature of the universe we live in. And physicists, are pretty disappointed that hints of the supersymmetry or the grand unified theories that Paul was alluding to, the simplest ones have been ruled out, or the simplest or the most elegant ones have been ruled out. And we could have a whole debate on naturalness in physics and theory, because that's a big subject too. But it's been pretty slim pickings at CERN the last few years, which is why these results we're talking about are so exciting. And just as an aside on the nature of why we're looking to particle physics and particle experiments, not necessarily with accelerators, many are in deep mines, to solve the dark matter problem, over the decades, by a process of elimination, essentially everything else has been ruled out. It's not black holes, it's not, wadded up socks in interstellar space, it's not rocks, it's not dust particles. There's a little window of primordial black holes, but pretty much that's been closed. And so, all the fingers for dark matter point to a new subatomic particle and extension, something not in the standard model. So it's a nice convergence. And so everyone's, keenly anticipating where that signal might come from and how it might come. And as I said, there's dozens of experiments with solid state detectors in mines that are using rather different approaches than the accelerator to look for dark matter particles, but it's a valid approach too. So could this be it? We've been waiting an awful long time. Dark matter evidence has been accumulating since the late 1970s. So it's about time. We just know that the dark matter outweighs normal matter by a factor of 5 or 6. So we need a particle that's massive and has a relic abundance, or is as abundant as protons and neutrons overall in the universe. So there's a huge number of these particles, but it's dark. It doesn't interact with electromagnetic radiation. And that ties one hand and maybe both hands behind your back when you're an astronomer. You can just look at its gravity on large scales. And things have, of course, got sort of desperate in the fact that we just eliminated things and don't know what it is. So people have been playing around with gravity. Modified Newtonian dynamics, MOND, has been, it's sort of like an egg stain on your chin that won't go away. It's extremely inelegant in physics terms in some way, because you could just tweak the force law of gravity by not very much, a few percent in the exponent, and you can get rid of the need for dark matter completely, right? Make it go away. Just change Newtonian gravity, which of course is not tested on scales beyond the solar system. So that's how dire it's got, that we're playing around with, very inelegant, kludges on gravity or other models that actually explain the data rather well. And we need insight from physics, basically, because the handles on physics. So to the question, which is exciting what Renee said, I mean, if the muon, experiments can turn into a whole industry of doing these kind of physics experiments, to me, it increases the odds that we really will, in the end, nail the dark matter particle by that route.
For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.